That we're done with that, huh? Okay, so we will be diving more into tree diagrams today, but I will collect these. Yeah, please pass those up. Sorry, I forgot to ask. While you guys pass those up, and you can write down tree diagrams. Do you guys remember when we did tree diagrams last week, Friday, in our sample space? No.
Yes.
You did not? Okay. Easy. Well, we'll be using them then again today. So the difference is that on Friday we were just like practicing drawing them. Like today they actually become useful for calculating probabilities. Here's a stat box if you haven't already drawn it. So then the tree diagrams, we use those to represent compound events when the number of outcomes is not excessive. So if you recall, on Wednesday we talked about compound events, how two different things happen. And you guys remember from Wednesday what we do to find the probability of a compound event? Multiply them. So that's still true today. But what we can do is actually like use those tree diagrams to illustrate those different events happening and use that to figure out what it is we're multiplying. It kind of keeps things organized. So as I told you guys last Friday, I'm not the best at tree diagrams, so I'm working on drawing them in a more organized manner. The thing is when we draw our diagram, the probability is on each branch. So if we go back to the starburst example that I used last week, the probability of picking a pink starburst would be listed on the branch. We couldn't, like the example wasn't really complete for us to calculate that, but that's what you would do. So if you had a 25% chance of picking a pink, then you would put the 0.25 on that branch, whatever that value is. And as we already mentioned, to get the given outcome, multiply the probabilities of taking the branches to get there. So that's where the compound comes in. Whatever the probabilities are on that branch, you would multiply those values to get that compound probability. So today we'll be focusing on independent events, so we don't have to worry about the dependent events until next Monday. Well, Monday when we will kind of use the tree diagrams to illustrate those types of situations as well. We're going to jump into an example where we'll make the tree diagram and then we'll do two different problems with it. Are there any questions? Yes? I don't think it's worded the best, but it's just when you multiply the different parts of the branch, like it's just like multiplying the probabilities like we did on Wednesday is basically what it's saying. So I don't know that you need to write it. I mean, honestly, you could just say multiply the probabilities. Like that's probably enough. So here's our example. So the class is broken down into males and females. It's a math class. 60% of the students are female. And then 30% of females have a graphing calculator, and 20% of the males have a graphing calculator. The first thing we'll do is make that tree diagram. So I'm going to give you guys a chance to get this written down, and then we'll go through how we would construct that tree diagram, and then fill in the probabilities. when we look at our class and we pick a person at random, to start with, there are two options. It's split up into girls and boys, or males and females. So we would start our branches like this, going female and male. We'll go back and fill in the probabilities. We're just going to draw the branches first. After that, when we go back, they're divided into they have a graphing calculator or they do not have a graphing calculator. So let's say that G is graphing calculator and N is no graphing calculator. Or you can write a full word, like there's nothing stopping you if you don't like my notation. Write something that makes sense to you. And then the males are also split up that same way, where they either have a graphing calculator or they don't. A lot of times in your assignment, the tree is started for you. So if you're having some struggles, just pay attention to that. I know on your assignment there's one that actually has 3 branches and then 2 branches and things, so just kind of pay attention to those. Now we have to put in our probabilities. So we've got 2 choices. It's really a personal preference. Do you want to put your probabilities in as decimals or as fractions? Okay, and I don't care. Just do remember you have to be able to go between both, because I noticed myself, I kept going decimals, which is not my norm, but I kept being like, okay, I want to use decimals, and then the answer in the back would be a fraction, so I'd have to make sure I could convert that to check my answers. So I'm not going to grade you up either way. You choose what works for you. The reason why I went decimals is I was thinking, okay, 30%, that is 0.3, and like that made sense to me. But again, you could do 30 over 100, right? And I forgot 60, that was first. So 60% then is 0.6, and 20% is 0.2. So use those or use fractions, does not matter to me. So now we'll put the numbers on the branches. So 60% were females, so that's 0.6. Like, don't put the percents, choose a decimal or fraction. 30% of the females had a graphing calculator, so 0.3 will be on this branch because it's the females with graphing calculators branch. And then the males with graphing calculators, I have to go down the male branch and then the graphing calculator branch, and that's 0.2. We still have to fill in the other branches. What I did in blue is what was given to me in the problem. So each set of options has to add up to 1. Whether you have 2 options, 3 options, 4 options, I don't even think you're going to see 4 on your assignment, it's usually 2 or 3. It has to add up to 1 because 1 remembers the total amount of things that could happen. So if 0.6 is the probability for female, what would be male? Yeah, 0.4. So these 2 have to add up to 1. If you did fractions, it's the same way. They have to add up to 1. So now these are our 2 options. So these 2 have to add up to 1. So 0.3 and 0.7. So they have to add up to 1. So not all 4 of these, just this. Because if it's a girl, this is 100% of the girls right here. These 2 add up to 100% of the girls, so it has to add up to 1. These 2 add up to 100% of the boys, so they have to add up to 1, so that's 0.8. Does that make sense? I just really want to make that clear. And if there was a third option, then you'd have to make sure all 3 add up to 1. So that's the tree diagram piece. Now that we have the diagram, we can start working with probability. But are there questions on how to fill that out, how we got the numbers, why we put them where we put them, or anything like that? Okay, I'm going to make sure everyone has got this down before I keep going. So then the question is, what is the probability that a randomly selected student is male and does not have a graphing calculator. So I do have to multiply both parts. So it's 0.4, 0.4 for the chances that the student is male, and then 0.8 for the chances that the male student does not have a graphing calculator. So just like on Wednesday, we have to multiply the compound probability because it's male and no graphing calculator. So I end up with 0.32, or just for those of you that use the fraction route, in case we got people watching the video, we got 8/25. We did fractions the second hour. There's one other kind of thing that could happen, so we'll talk about that. Still using this example, but just another question. Are there any concerns about how we can use this? Okay, so I'm going to leave my tree up here and go on to the next question. What is the probability that a randomly chosen student has a graphing calculator? How many branches result in students having a graphing calculator? There's 2 branches, right? Like on the previous question, there was just one branch that was male and no graphing calculator. Now we've got 2 branches because you could have a female with or a male with. When you have more than one branch that could get the outcome you're looking for, you have to add up the probabilities. So you're still multiplying the compound probabilities, but then you're adding up both different options. So for example, let's go with female first. So female with a graphing calculator would be 0.6 and 0.3. Male with a graphing calculator would be 0.4 and 0.2. So we have to add them. You have to add all of the branches that give you that outcome you're looking for. So even if, like, this is a pretty small tree diagram, so you might have some with more options, you might have to add 3 branches together, but however many branches end up with that outcome you're looking for, you add them together. So here we've got 0.8 to 0.18 plus 0.08, which is 0.26 or a 13. So when there's more than one branch that end up with your outcome, you have to add both of those. We're going to hit the stat box up, but are there any questions about this stuff? So I was really struggling with how to word this, so this might not be worded well. But each time our outcomes branch out, what should the branches add up to? 1. Okay, so you get what I'm going for? Yeah. I was asking second hour, like, how do I word this better? And that's the best I could come up with. Okay, that's it then. So there's still a decent amount of time left. If you've got questions, let me know. Especially if you have questions also on